This video will cover flip-flops as counters, data latches, and shift registers. Flip-flops are commonly available as discrete devices and also as building blocks in many types of integrated circuits. Basically, a common flip-flop produces an output voltage that is either high, usually plus 5 volts, or 0 volts, depending upon the combination of conditions at its inputs. We will talk in general terms about how they function and some of their important applications. I've given some references at the end of this video if you'd like to learn more about the different varieties and how they function in more detail. I will not say much about the inner workings here, other than the fact that they're commonly described as combinations of logic gates. Furthermore, logic gates themselves are constructed from combinations of transistors integrated onto a single chip of silicon material. Flip-flops are usually represented schematically with a rectangle, with several inputs and output lines. In this drawing, the outputs are represented by Q and Q bar, also called Q naught. Q bar has the opposite state to that of Q. So if Q is plus 5 volts or high, then not Q is low or equal to 0 volts. The corresponding logic levels are 1 and 0. So if the Q goes to 0, the Q bar or Q naught goes to 1. The J input is called the set pin. When J is 1, then Q is set to 1 or 5 volts. Input K is called the reset pin. When K is equal to 1, Q is set to 0. When both J and K are set to 1, the output Q toggles between 1 and 0 whenever a 5-volt pulse appears at the clock input. Only the rising edge of the pulse, the transition between 0 and plus 5 volts, will trigger the change. If we string several of these flip-flops in a series, linking the clock of the following device to the not Q output of the previous device, we can make a binary counter. Imagine that a 5-volt pulse enters the clock input on the left. First flip-flop recognizes the rising edge of the transition and changes QA to high, or plus 5 volts. If QA goes high, not QA must go low, or 0 volts. What happens at QB? The trigger for the second flip-flop is not QA, but it made a falling transition, not a rising one, so QB does not change. Let's go through another clock cycle. At the rising edge of the clock input, QA will change. It's already high, so it goes low. Not QA has to do the opposite, so it goes high. The rising edge of not QA is a trigger for the clock of the second flip-flop, so QB must change. It goes from low to high. Another rising edge at the first clock input makes that flip-flop change its state. QA is low, so it goes high. And not QA goes low. Since the input to the clock at the second flip-flop is going low, that is not a trigger, so QB stays high. At the next rising clock edge, QA goes low. Not QA goes high, and that triggers QB to toggle high to low. Notice that QA changes at half the frequency of the clock. For example, if the clock is changing at 8 pulses per second, the waveform at QA is half that speed, or 4 pulses per second. And QB is half QA, or 2 pulses per second. Here is a counter with 4 flip-flops. It is a 4-bit counter. It can count up to a 4-bit word. Let's evaluate the count at various points in time. Each flip-flop represents a digit. A high state represents 1, a low state represents 0. A vertical line tells us the status of each flip-flop or bit at that stage in the count. The most significant bit, the digit with the highest value, is represented by the last flip-flop on the right, QD. The least significant bit is QA, so our binary value is read up from the bottom to the top, or DCBA. After one clock pulse, we have, from bottom to top, low, 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 high, or 0, 0, 0, 1. After 4 clock pulses, from bottom to top, we have low, high, low, low, or 0, 1, 0, 0. That is a binary value for 4, just as we would expect if our counter is counting clock pulses. Pause the video and read the outputs and number at this point. We have low, high, 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 or 0, 1, 1, 1. That's 7. This arrangement of flip-flops is known as a data latch. It can read the binary values on a parallel group of wires or pins from another digital device and store them. For example, imagine that we have a counter that has just completed a job of counting to a specific number. Now we want to capture that value and store it temporarily before handing it off to a computer. Perhaps we need to free up the counter and let it go back to count another sample. The counter has several different outputs, each representing a different bit. Together, these bits constitute the binary form of a number that represents the information that we would like to use. In this diagram, we've connected the output bits of the counter to the data input lines, D0, D1, D2, and so on, of a data latch. When the data on the counter is ready to transfer, plus 5 volts is applied by some control device that's not shown here to the clock inputs of each flip-flop. The voltage enables each device to match its output Q to the logic level at its respective input D. The clock remains in the high state only briefly, so after the reading interval, changes that appear at D do not affect the value of Q until the system is ready to transfer another number. Hence, the data is captured in the latch before transferring to a computer interface or another device. So we transfer all bits at once in parallel from the counter. Another very useful application for flip-flop devices is called a shift register. A shift register can move a binary number in a serial fashion along a single wire. This diagram represents the first 3 stages for a shift register. All information comes into the first stage at the data input D. Each of the other flip-flops gets its data input from the output Q of the previous stage. Each flip-flop receives the same clock pulses. Each flip-flop reads data at the rising edge of the clock pulse. It's very important to note that it takes a few nanoseconds for the output Q to switch and agree with the data input D. So at time t0, each flip-flop reads the logic level at its D input, but that value does not appear until a few nanoseconds later at t1. If that were not the case, every flip-flop would have the same value as the first flip-flop. Let's see how this works. Let's imagine that before any clock pulses, all of the outputs are set to 0. Now imagine that the logic level at D for the first stage becomes 1, and a clock pulse arrives. After a few nanoseconds, Q0 also changes to high, but it's too late to trigger the next stage. Q1 remains at 0. The second stage reads the value of Q0 as it appeared just before the most recent clock pulse. All of the later stages also read 0 at their corresponding inputs, and their outputs remain at 0 as well. Let's imagine that D at the far left goes low, and a second clock pulse arrives. A few nanoseconds later, Q0 also goes low. The second flip-flop reads the state of the first immediately prior to the clock pulse. It was high, so Q1 goes high. All of the following stages read 0 to match the state of their predecessor just before the clock trigger. At the next clock pulse, the data in the first stage is still low. Q0 remains low. All of the following stages read their appropriate inputs in the same manner as before. The effect is to take the Q values in the row in the table immediately above and shift everything one column to the right. The pattern continues with each new clock pulse. A new data level comes in at the left, and one bit at a time, everything else shifts to the right. At the far right end, the data can be shifted into a computer interface or other device. The shift register plays an important role in reading out data from cameras and diode arrays and instrumentation. If you're interested in more, here are a couple of good references you can find online.